Yes. Can you hear me?
Yes, we can hear you.
Okay. So good morning again, and so I'm wait. I share the screen. Okay, so I am Ivan CARNIMEO, and I work at SISSA on the development of the GPU version of the Quantum Espresso code. So now we are going to have the hands-on, in which we will see a few practical test cases, trying to work with the concept that Pietro gave us in the theoretical lecture a few minutes ago. Let me start. Just let's recap. Let me say a few general things about the hands-on. So from what Pietro said in the before, we learned that Quantum Espresso is a big code that has a big parallel part. So the speed up of the code, according to the Amdahl law, depends on the sides. Is conditioned by the serial part. So we have a serial part, a parallel part, and the parallel part is implemented using different approaches and strategies. So Pietro spoke about MPI, that is the message passing protocol, and has several advantages, such as distributing the memory. So NPI is the preferred choice of parallelizing Quantum Espresso because it allows to distribute memory among a large number of nodes, and this allows to treat large molecules, because for large molecules we need a lot of data to be stored and to be kept in memory, and this data can be distributed among nodes. So in this way, that's why MPI is very used, is the basic parallelization protocol in Quantum Espresso. We also have Openmp, which also helps in distributing the workload, but it is a shared memory approach, and we will see a few examples in the following. And we also have GPUs. So in this hands-on will be divided. The first part will be about HPC, so how to optimize calculations in regular HPC clusters based on CPUs. And the second part, it will be working with GPUs. Other important things that Pietro said is using endpools and NDAG. We will see a few examples in the following. So how to optimize running calculation with pools and NDAGs. So let me say one thing. All these strategies and approaches have been developed in order to treat large systems, to optimize running, to optimize the execution of your test cases and production calculations. So they are meant to work to accelerate the calculation, especially when you run large systems. So for this reason, here in the hands-on, we will not see drastic improvement of calculations from the test we will do, because we are forced to work with small systems, because we are many people, and if 100, you are more than 100 participants. So if each of you runs calculations using 5-10 nodes, we go out of computational resources. So we thought you will be running small test cases. So please, when you run test cases, focus on learning the general approach, on learning how the calculation how is the setup. Try to understand the concepts. And of course, you will not see drastic speed ups, and not always, at least, because we are quite limited by the fact that the calculations are small. Anyway, if you learn this procedure, maybe you are able to run more efficiently calculations using Quantum Espresso on your own production cases. So if you have to write an article, if you want to do a test, if you want to learn about a new material with Quantum Espresso, hopefully after this hands-on, you will know how to optimize the calculation, how to run a large and to fully exploit the computational architecture on which you are running. In order to give you also an idea of what happens on large systems, since the test cases are quite small, I will show you a few slides after each exercise to show what it means, what you have done, and how what you have just done on the small case is reflected on a large test case. For this reason, I would like to go synchronize with you. So my idea is that you try as much as possible to follow me, and I will wait for you all while you do the exercises. And so yes, let's try to go together. And I will try to wait for all of you to have done the exercise as much as possible, and don't this said, I think we can go, we can proceed. So the covered topics of this and so on are basically 5 exercises, which are quite, the first one is preparing Quantum Espresso CPU version. So you compile Quantum Espresso using different libraries and the libraries that Pietro explained us before. Exercise 2 is how to use Quantum Espresso on HPC architectures without GPUs. At exercise 3, let's see, if we have time, I will explain you a few things about GPU, how GPU work. So very basic things about GPU programming and GPU setup, just to let you understand why we are using GPUs and what is the improvement that we might have. And then exercises 4 and 5 are similar to 1 and 2. So exercise 4 is let's compile Quantum Espresso with GPUs, and exercise 5 is let's run calculations using GPUs. First of all, for this and so on, of course, we cannot run neither in the laptop, in the virtual machine. First of all, because this and so on is about HPC calculation, so it is very unlikely that you will ever run HPC on your laptop. So we need to run on a cluster, and we will be using the Marconi M100 cluster for this. First of all, please connect to the HPC cluster. Yesterday, you have received an email with the credentials, and also I've seen on the Slack workspace that most of you have already tried the connection. So now I would like, in order to try to stay synchronized, I would like to ask you to connect to the cluster with the credentials you have already received. And when you are ready on the cluster, raise your hand so I can see, I can check how many of you are good. But so let me, okay, now I have the window here. Okay, so let's check. So please connect to the cluster with the SSH, this command here. This instruction, you will find these instructions also in the readme.md file in the day 9 folder. So please connect to the cluster. And once you are connected, raise your hand so I can see how many of you are. So yes, keep 31. If you have problems in the connection, you can write on Slack, or yes, and yeah, of course you cannot raise your hand because now we are using it for a different reason. So we have we are now 31 people. Okay, so I assume that, so now I see 32 raised hands. So I assume that about 30 people are trying to follow the exercise in synchronized. So, okay, so good. So once I cannot raise hand, it seems to take a lot of time to me and a few others. Okay, so if you have connection problems, if the problem is your own connection, I'm afraid we cannot do anything for that. But you can, so then you can, I think you can still follow the exercise, and yes, it's okay. So okay, about 33 people plus someone else who cannot have okay. So for those who don't, I'm not able to raise hand, but connected successfully. Okay, good. So in order to follow the hands-on, I suggest you to refer to the README files in the repository. So once you are connected to the to this cluster, you can you will find this this directory in your home. So when you are in your home, you can do cd. So now lower your hand. Everyone, you can lower your hand because we can proceed. So once you are in your home directory of Marconi Centro, Marconi 100 cluster, go inside this directory and type git pull. In this way, you will update the repository in which the files for the exercise are kept. So you will download the last version of the repository. So do this git pull. And once you have updated the repository, then you will see all the README files, the updated versions of these README files. And you can, if you open them, you will find pretty much the same instructions that I will tell you here with the slides. So if you don't, if you open, I suggest you to follow the hands-on and to try the hands-on by looking at the README files, because they are the most updated version of the hands-on available at the moment. So please lower your hand. Lower your. Yes. Don't. If you have questions, just ask on Slack or yes, here in the chat. So one thing is that since now we are working on a really huge cluster, and even if you in the future will work on clusters like that, so it's not very, at least in this case, it is not very advisable to work in the home directory, because these types of clusters, since they are engineered for many users, so usually the home directory is quite smaller, and it is often backed. So the home directory, usually the good practice for working on those clusters is that in your home directory, you keep the important files that you really need, because usually the home directory is backed. So in case one hard drive is broken, the data are not lost. But in order to run calculations, this cluster has another partition, which is called the Cineca Scratch partition, which is it is better for calculations, because usually calculations produce many files that are not for example, they write the wave function or temporary files. So, and the size, the dimension grows. There are many files, and so if you run calculation from your own directory, you will soon get out of memory, disk storage. For this reason, the good practice is to move to the Scratch partition, run calculations from there, and then copy the important files, the output files, to the home directory again in order to save them. So for this reason, after you have done this git pull, that now I assume that all of you have done, because it was not a long lasting command. we do this other command. We copy -r, it means recursive, so we can copy an enter folder. So we copy the directory. So before you did the CD, so you are inside this material for Max School Online School directory. We updated the directory, then we copy day9 directory to this $cineca_scratch. So we are copying the directory of day9, so where our input file, job scripts, to the Scratch directory, because Scratch directory is the directory from where we want to work. After that, you do cd Cineca Scratch, so you are moving yourself to that directory where you have just copied the files, and you go inside day9, because this is the folder that you have just copied to Cineca Scratch. And then just to check, type pvd, and you should find here m100_scratch. So if the result of the pvd is this one, it means that you have done things correctly. So please raise your hand where you are done with these comments. Okay, now I see 20. Before I could see about 30 people. Now it's 24. So I assume that a few people done. I see. Wait. Is this PDF available? Not yet, but of course I will give you the slides in the next after the end of this answer. So at the moment you don't have this PDF, but you will. CP is not working. The warning, it is a CP -R, because you are moving the entire directory. So don't forget this -R. Otherwise, it will tell you that it's not working because it cannot find files. So I see. Okay, now I see again about 30 people, which are the same number of people as before. So I assume that most of you have done. I see other confirmations here, so we can proceed. So most of you now are in the right partition, and we can start with exercise 1, which is preparing an installation and working version of Quantum Espresso. Let me say a few things. Let me just recap what Pietro said before. So I think from a practical point of view, there are 3 things you should keep in mind when compiling a version of Quantum Espresso. The first one is the compiler. Usually, there are many Quantum Espresso can be compiled using several compilers. I think the most, maybe the most. Sorry, you can lower your end now. Lower your end. So the compilers, you have many options. The most popular ones is Fortran, of course, which can be downloaded for free. And if you are on Ubuntu, you can even easily install it with the apt-get install. Another option is iFort compiler, which is the Intel compiler. And we also have MV-Fortran. MV-Fortran is, you might have known it with its previous name, which was PGI. In the last year, I guess in the last months, I think last year it was renamed, and now it is MV-Fortran. So MV-Fortran is the compiler which was previously named PGI. And also, if you have ARM architectures, you have Flang. There are also other options, but I think these are the most common ways, most popular ways. So the Quantum Espresso is written in Fortran, so you need the Fortran compiler, and these ones are the most popular ones. So of course, if you are trying to compile Quantum Espresso on your laptop, then you can do basically whatever you want. You can download the Fortran from Ubuntu repository, or you can download iFort or MV-Fortran. You just choose, you download, install the compiler, and then you compile Quantum Espresso. If you are working on an HPC cluster, then you should ask the you should check which compilers are available on the cluster. For this, in this exercise, we will be using MV Fortran. The other two important things keep in mind is how to perform calculations. The most relevant part from the mathematical operations is linear algebra and fast Fourier transforms. So we need libraries for doing linear algebra operation, matrix-matrix product, diagonalization, QR decompositions, stuff like that, and libraries for doing fast Fourier transforms. Of course, if you don't have any external library installed on your system, Quantum Espresso provides its own version. It has internal own version of both linear algebra libraries and fast Fourier transforms libraries. So with a minimal setup, the minimal setup requirement for installing Quantum Espresso is just having a compiler. And if you don't have any other external library, Quantum Espresso will just use its own internal ones. So internal BLAS for linear algebra and internal FFT for fast Fourier transforms. However, there are other options. Other very popular options is Openmp, which is also a free library that you can easily download, for example, on Ubuntu system with an apt-get installed. And also there are MKL. MKL are usually a bit faster than they are very fast, and they're a bit faster than the other options. So they are advisable in case you have them, but they work only on Intel and AMD processors, CPUs. In this case, since Marconi 100 is based on IBM processors, Power 9, we cannot use MKL. For fast Fourier transforms libraries, you also have this FFTW3, which is a very fast library for fast Fourier transforms, which is a good option. Or even also MKL have their own version of, there is an MKL version for fast Fourier transforms, but again, they work for Intel AMD processors. So in this exercise, in this hands-on, we will use FFTW3. So let's see how to set up things, how to do this. So first of all, you go CD, you go inside the first directory, exercise 1 CPU setup, and you download the source code of Quantum Espresso from the repository. Of course, I suggest you to copy and paste this command from the readme.md file that you will find in the folder, in the exercise 1.cpu setup folder. You will find a readme file. You can open it with BI or with another. I'm not sure there is MaX in Marconi, so but you can also cut it to the screen or less. You can use less. Or even I think you can open the README file from your virtual machine or from your laptop and copy and paste the command to the shell on the Marconi cluster. Anyway, I think from there it is easier to copy this URL here. So when you run vget and with this URL here, you will download the source code of Quantum Espresso as an archive. tarbz2 is an archive. So at the end of that command, you will have this file QE 6.7 max release tarbz2 in your current folder. So if you log ls, you will find this file. So since this is an archive, we have to unpack it. So tar xjf, this command is meant to unpack the archive here, the tar file. Once you have done it, you can just rename the folder for your convenience, because now it is easier for you to browse inside and outside. So move this folder. This folder is created by this command here. So after you run this command, you will have this folder created on your system. You can rename it with QE CPU and go inside QE CPU. Once you have done it, you can load the environment. So we can load the libraries that we will be using to compile this version of Quantum Espresso. So in the cluster, in the cluster there is a module system. So with module purge, you just remove all previously loaded modules files. So you clean your environment. Then we load only the modules that are needed for the compilation. And with this compilation, we will be using HPC Sdk. So this library is the library which contains the compiler, the MD Fortran compiler, which is the one that we will be using for compilation. So you load HPC Sdk, and here inside you find the compiler MD Fortran. Then you load Spectrum MPI, which is an MPI manager for running parallel calculations. You load FFTW. This is the library I was telling you before, for FFTW3 fast Fourier transforms. So once you have run this command here, now your system is set up. So you have loaded all the libraries that are needed to compile Quantum Espresso on the cluster. And so you can run this command /configure with this option. Once, please do it. And once you have done it, raise your hand again. I can also do it on my, so I can show you. So now I am on the M100 Scratch partition. This is my username. So I go inside day 9, which I already moved before. I go inside exercise 1. I have already, I have this archive that I previously downloaded with the bget command. So I have this directory here, and here inside there are all the folders coming from Quantum Espresso. So I run configure, and with this option MPI. So this is what it should happen. But I see that you are going much faster than me. See, it's good. So 9 people with raised hand, please. So when you run that command configure, raise your hand. I see 12 people now, 14, 16. Let's go on. Done. When I do module, nothing happens. It is normal. Amal, it is normal. When you load modules, it's just that you have loaded them. It's fine. Done. Good. 23 people. Before we were 30 people, so I expect that a few more people should accomplish this. So please raise your hand once you have run this configured script. We are still 23. So let's wait a few more minutes. It shouldn't be difficult. I tried yesterday I tried really to copy and paste commands from readme.md files, and everything seems to work. So if you are you shouldn't find particular problems with this. I see 24 people, so I think that 25, so I think we have still 6-7 people working on it. Okay, in the meanwhile, I can explain you. So when you run configure, so this command, so let's recap. So we have modules. So we have loaded modules. So in this, if you type a module list, you will see which module are loaded on your system. And in this case, we have HPC Sdk, so the compiler, Spectrum MPI, and fast Fourier transforms. So once you do this, then with configure, it's just you are asking Quantum Espresso, okay, I'm about to compile you. Which libraries do you see? I have loaded my libraries. Do you see them? And Quantum Espresso is answering you, yes, this is what I see. I can find BLAST libraries for linear algebra, and I can find LAPACK libraries for linear algebra again. And here it is telling you that the linear algebra libraries will be taken from HPC Sdk. So it means that we will be using linear algebra libraries that are already provided with MB Fortran compiler. And here it is also telling us that it is using FFT libraries, FFTW3, which are the libraries that we wanted to use and that we loaded with this module now. So now everything is fine, and we can compile the code with make -j4pw. So do it, and let's wait a few minutes here because it will take, I think, 2 or 3 minutes. So you can lower your hand now. I'm not sure that you will all be able to compile the code, but not because it is not working, but because we are many people running on few nodes. So it might be that it can go slower or faster or maybe so, but don't worry about it. The important thing is that you have learned how to load modules. So the important thing now is that you have learned which are the most important things to compile Quantum Espresso, compiler, linear algebra, and FFTs, how to load modules from the HPC system, how to configure the code, how to configure the installation, and how to run the installation. So at this moment, if you tried, okay, I see that it is going very slow even to me. So maybe it is because many of you are running this command, and the cluster might slow down. But don't worry for this, because for the next exercises, yesterday we compiled one version of Quantum Espresso, which we are sure that is working. So for the next exercises, we will use this version, which is already compiled. So even in case you cannot accomplish the compilation now, don't worry. The important thing is that you learn how to do it and that you understood what we have done so far. So you can lower your hand now, please lower your hand, because, and let's wait, yes, but let's wait a little bit, but
excuse me, Ivan, somebody
yes.
said that you are going fast.
Am I going too fast?
Somebody tell.
Okay, so now we have a few minutes waiting for the compilation, so you can use them to do the exercise. In case you can also skip the last passage, so that make -j4pw. If you are late, you can even don't do that, because it's just a mechanical thing. The important thing is loading modules and configuring and seeing what happens after the configure. And after that, when you launch the compilation, usually you are not getting any problem from that, usually. So I assume that you are running that. Let me check in the chat. Ignacio, it means that you compile. Yes, for those. Okay, we have one person who already compiled pw.x. This is good. What is J4 flag? This has been answered. I could download with big F, stays temporarily unavailable. So maybe this can be fixed in a breaking room. If you don't have BGET on your system, maybe it is worth solving it inside the breakout room. Sorry. Oh no, I managed. Okay, good. So configure. Thank you. What is the option? Done. I don't see particular problem here. So yes, I think the cluster is. Maybe we can wait a few minutes more. So for those of you who managed to build the PW executable, you can do the next step, which is written in the README file, and is this one. So try running this calculation. Of course, the calculation will not be accomplished because you have not pseudo potentials here. But even if you see the error message, hey, I cannot find pseudo potential, it is because that PW is working, because that error message is sent by PW, which means that it has been compiled and it is working. So forget about the error message now. Just try this is the executable you have just compiled, you have just built, and if you will find the executable in PW src pw.x, and yes, if you try that, you will find an error message from the pseudo potentials, which is fine because it means that the PW is working. So in my case, I'm still compiling. I hope that most of you will do this. Okay, maybe please raise your hand again for those of you who managed to compile pw.x. So for those of you who managed to when the compilation finishes, raise your hand again. Yeah, so 2 people. Unfortunately, I think that this is going much slower than usual because we are many people on the same cluster node. So it's I think it is going quite slow. In fact, usually if you are alone in a system architecture, you can compile using even more than 4 processors. Now we use that -j option, which means that we are compiling with 4 processors. But of course, you can compile with 1 processor and it goes slower. But you can also, don't do this now, but if you use -j without inserting any number after that, so just make -j pw, it will use all available cores. Please don't do that now, because otherwise you, for sure, nobody else will be able to run the compilation. So I see that it is going very slow because, yes, there are many people connected. So I think it is better if we move on, otherwise we cannot do the other exercises. So yes, I suggest you can try the compilation on your laptop, for example, if you have the compiler. So you can just apply what we have learned here on your laptop. And maybe we can stop it now. Let me just check if at least I can finish the compilation so I can show you the end of the exercise. But I don't want to spend too much time on this, otherwise we don't have time to do running calculations. So yes, so Control-C and you interrupt this compilation. I'm sorry, but the problem is that I don't want to waste too much time on this. So please lower your hand and note what you have done so far, and so interrupt the compilation with Control-C, like this. And let's move to exercise 2. So exercise 2 is how to run calculations exploiting HPC cluster architecture. For this very complex architecture, there is usually a job scheduler, which means that if there are too many people sending jobs at the same time, there is a manager that queues the jobs in such a way that if I send a job but all nodes are occupied, I will wait until one of the nodes is free, and then my calculation will go. So all this stuff, this is this queuing system is managed by a manager, which is called SBatch. And we need to submit a job script to this batch system in order to run calculation. So this job script is here, and you will find it in exercise 2 directory job.sh. So you can see this file exactly in your folder. And this job seek is divided in two main parts. The first part is our directive for batch manager. So we are telling how many cores do we need, how many processors, how many memory do we need, and other stuff like reservation and account, and so everything has been set for you. So don't change these fields. Just in order to let you know. Of course, the processors are organized in nodes, so we are asking now 1 node and 16 processors per node. So each of you will be running using 16 processors from the same node. And here, this manages the MPI processes. And here we have this other command, which manages the number of Openmp threads that are on which we are running. Here, QA root is the path to the executable. So if you managed to compile your own version of Quantum Espresso, you could have inserted here your path. So if you just substitute this string with your username, you should be able to point to your own version of Quantum Espresso. If you didn't manage it, as so I didn't do that. So just leave as is, because this version of Quantum Espresso is a version that we compiled yesterday, so it is working. So don't need to change this field. Just I want to let you know that this variable points to the version of Quantum Espresso that you have a working version of Quantum Espresso. So let's use this one. This is the job script. Now you just send this job script using this command, sbatch job.shell. So you go, I will do this, you go in the exercise 2 directory, you will see the README file here where you find all the instructions, and the job.shell file here when you see just the job I have shown you in the slide. And it is enough to send sbatch job.shell. It will tell you submitted batch job, and this is your job ID. So it means that job submission has gone, and you can check the status of your job with this SQ minus U user ID. So my username is this. Sorry. So I submitted my job with sbatch job.shell using that job script, and this command sq minus u is telling me your job is running because the status is running. So the cluster is doing the calculation, and your job ID is this, which is the same as this one. And I am running on one node, and this is the node on which I am running. So if it is still running here, you can do this. So please submit this job. Okay, so I see that 30 people submitted this job, which is good, which means that pretty much all of you are working. So in the meanwhile, let me explain. So this job is running, it will take a bunch of minutes. So in the meanwhile, while the job is running, let me explain. So here we have sent one job, which is this input file, using one pool and one NDAG. If you remember from Pietro's lecture, pool, it means that we are basically pool equal to 1. It means that we are not exploiting any parallelization over k points. And NDAG 1, it means that we are not distributing the matrix for diagonalization. At the moment, this is our basic job. Here, this input file name, you can choose whatever name you prefer. I just choose this one because if you change one of these parameters, then you change the file name accordingly, so you will keep track of what you are doing on this system. I think we can gain some time. So while these jobs are running, I think we can go further just to explain things. And this exercise is about pool parallelism. So now we have sent this job with one pool and one NDAG. And in the next step, we will send more jobs using more pools. So 2, 4, 8 pools and the same number of NDAG. So it means that this exercise will show you how to practically exploit pool parallelism. If you see inside this input file, you will see that this input has 8 K points. So if we have 8 K points, the reasonable number of pools to split them is 2, 4, 8. If we split 8 points in 2 pools, it means that we will have 2 pools, 4 K points each. If we split with 8 K points in 8 pools, it means that we will have 8 pools, 1 K point each. And this will be assigned to groups of processors. So at the end of the, when I just go on to I don't want to waste time. So once we will be done with these output files, we will see that these computational times will be like this. So increasing the number of pools will result on a reduced computational time. And this is because, as Pietro explained in the morning, increasing the number of pools allows us to reduce communications among MPI processes. And this is very useful because, as we have seen before, MPI has the great advantage that they allow to distribute memory and to parallelize the parallelizable part of the code, so to parallelize the workload and distribute memory. But they also have, let's say, a drawback, because the more MPI you use, and the more processes need to communicate each other, because you are splitting your data in smaller parts. So in order to have the final result, we have to gather all parts together. So processes need to communicate data among them. So for this reason, if you push MPIs too much, you will have that communications will saturate calculations. So pools is a good way to reduce the number of communications at fixed number of MPIs. Let's check how our calculations are going. Okay, now we have 43 people running here, and my run is still okay. Here it is still running. Is it? So we are at iteration 3. I think we have. Okay, here we will do just 4 iterations. So here it is. It is going, and of course you can check the number of K points from here. 2 times 2 times 2, it means 8 for 8 K points. And in fact, in the output file here, we search K point. Sorry, point, not K point. And here it is telling us number of K points is 8. So from here we get this information, and also at the beginning of the file we find again what Pietro told us about the computational resources, because in this case we are running on 16 processors. And if you look again in the job script, here we asked 16 tasks per node, and here we find 16 processors. So it means that we are running with 16. Yes, and of course, yes, we are running with 16 MPI processes. And here it is telling us that MPI processes are distributed on one node, which is here. We asked one node here. So in the output file, you can find some recap of your hardware configuration. So Yes, unfortunately, you see that these calculations take a while. The problem, yeah, it is what I was telling you before. The problem with this and so on is that these facilities are meant to treat large systems, and we have here 2 hours for the and so on and limited resources. So we have to find a balance between the dimension of the test systems. Anyway, I see that many of you are running, which is good because it means that maybe a few of you already knew a few things of this. So 48 now. Okay, while these calculations, and now I have, my calculation is almost finished because I have reached the iteration 4, which is the last iteration, because this in this input file we set this max step here is 4. So we are doing only 4 iteration of the SCF. And I think mine has. After I finish, I should change pool to 8 and rerun. Yes, after you finish running this calculation, if you read in the README file, so after this calculation, now we are running this calculation with npool1 and ndiag1. After that, you can change the job script and you can add these lines. Of course, you change from npool1 to npool2 and npool2 here too. And then you can attach these other strings here. So the basic idea is that we prepare a new job script after this one. Okay, so my calculation now has finished. So if I see the output file here, I will get job done here and the computational time here. In this case, the good, you will see 2 times at the end of the job, CPU time and wall time. Usually, the most reliable one is wall time, because wall time, CPU time is just the time in which the CPUs were really working. And also, if you use GPUs, that CPU time is not something that is wrong, because the workload will not be on CPUs but on GPUs. So always refer to the wall time when you want to check the execution time of the latency of your job. And also wall time keeps also into account communications and input-output streaming, so it gives a more complete view of the job of the job execution time. So here the job took 9 minutes 35 seconds. So yes, I think this is done. So the next step is you can find this instruction in the README file. So I will do just the same as written there. So I open again my job script, and here I want to try pool parallelization. So I set mpool to 2. Sorry. And I also change the output file accordingly. And then I can also use the same job script to run npool 4 and pool 8. And pool 4 and pool 8 here. Save this job. And so npool 2 Pool 1, we have already done it. Now we have Pool 2, Pool 4, Pool 8. We can put these commands in one job script, write and quit, and again we batch job script. So I can see my new job that is running here. And if I log in the directory, I see the new output here. So the first one was the first calculation was the longest one. So the next calculations, of course, will take shorter time. I think yes, it will. We still have to wait a little bit because we are running 3 calculations now. But at the end, if you check the wall times, so you have wall time here at the end of this file, and then you compare with wall times at the end of the other files you will be getting in a while. So Pool 2 and Pool 4, you can plot them or just check them, and you should find a trend like this, because increasing the number of pools is decreasing communications at fixed number of MPIs. So in all cases, we have used 16 MPIs, and this has not changed. This is fixed. But using one pool, MPIs are communicating very much with each other, whereas using 8 pools, the communications are slowed down. So when I think you are running, because I think I don't see any particular issue. Okay, 39 people are running. So I think while our calculations are still running, I can show you something about why it is working. What are we doing now? I think you have already, this is pretty much similar to what Pietro told us. Let me just, so Pietro already showed us that the wave function can be represented in a 3-dimensional, as a 3-dimensional matrix, let's say, because the coefficient, here we have our orbitals that are expanded in plane waves here, and each plane wave has its own coefficient, and these coefficients have 3 indices. So G is the plane wave vector, the indices of the plane wave. I is the index of the constant state, and K is the index of the K points. So we can represent the coefficients on which our wave function is expanded and in a 3-dimensional way. So the longest dimension is the number of plane waves, because of course we can easily, if you run large system, you can easily reach 1 million of plane waves. So these matrices are very tall. And then on the other dimensions, we find the number of constant states or bands and the number of K points. So each coefficient here can be seen as a point in this 3-dimensional matrix. When we do MPI, we are distributing the memory. It means that this matrix, the matrix of coefficient, is distributed among processes. But what happens here? When we calculate whatever property, for example, in most times, every time we need to calculate something, a potential, the full Hamiltonian, the kinetic energy, usually we are applying one operator to one orbital. This means that if we split the orbital along the plane waves dimension, we see that this core here does not have the entire orbital. And this MPI process here does not have the entire orbital. But the quantity I want to calculate, energy's density, depends on the, often for this reason, I need to sum along the plane wave dimension, because the quantities are usually computed on one complete orbital. So for this reason, the communications among MPIs are much more along this dimension, along the plane wave dimension, rather than along the other 2 dimensions. So if I split the wave function, the MPIs, if I break along the plane wave dimension, the MPIs will need to communicate very much among them. So let's make an example. If I split the wave function, for example, in 4 MPI processes, since the communications, most of the communications occur along this dimension, it means that all processes will need to communicate each other because none of them will have one single orbital. The orbitals will be split among the different ranks, the different processes. And so they will need to communicate with each other very much. Otherwise, if I use M-pool, pool parallelization, I'm still using 4 MPI processes here, so 4 and 4. But what is changed is the way I'm distributing the wave function. Because in this case, yes, I'm the one single orbital. Let's check here. One single orbital, so one stick here, is distributed among 4 processes. If you see how it's done in this way, one single orbital is distributed among 2 processes because the processes are used, the wave function is distributed along the K points, not only along plane waves. So it means that we have still the same number of MPI processes, 4 in this case, but in this case, using this distribution, the wave function here, one single orbital is split among 2 processes. In this case, it's 4. It means that in order to compute the properties, we only have 2 processes which needs to communicate, and we don't have the communication on, or better, we have strongly reduced communications in these other directions because the orbitals are split among 2 processes rather than 4. So for this reason, I hope that this can be clear for you. But this is the main reason why the M-pool parallelism is so efficient. So please raise your hand when you have finished this M-pool parallelism. Okay, a few of you have good. So I assume that people who now are raising hands have finished the jobs with 2, 1, 2, 4, 8 pools, and they have checked in the output file how long the calculation took, the whole time, and then they found that using 8 pools is faster than using 1 pool according to this plot. So yes, unfortunately, the calculations with CPUs are a bit longer. We will see in the next exercises that with GPUs this will go much faster. So we have still 36 people running, and I am running. It is still going with pools too. Okay, now I'm going to put, so here, for example, I can compare M-pool 2 with M-pool 1. And we see that here it was 9 minutes 35 with 1 pool and 8 minutes 10 with 2 pools. So, yes. Okay, so we have now 5 people who accomplished the exercise. So so I think now that you are still waiting for calculations. So I assume that most of you have submitted the calculations and you are waiting. So I think I can show you some another slide regarding pool parallelism here. So on the basis of what we have just said about pool parallelism, no? So let's take this slide. So here I can split the wave function among plane waves and among pools. There is one subtle thing to keep in mind. When you use pool parallelism, you have to think about how many K points do you have and how many processors do you have. Because, of course, you are trying to, you have to fit pools in processors group. So when you have to think about what you are doing, because the numbers are not always compatible. Let me show you an example here. So here we have a crystal, and this system has 30 K points. So we have 30 K points, and I tried these calculations on 5 nodes. Of course, this exercise is something that we cannot, it would have been nice to do with the hands-on, but 5 nodes each for 100 people, it is far beyond our possibilities. So I did it on myself, and I'm showing you the results here. So 30 K points, if I divide 30 K points in 3 pools, it is quite fine because it means that I have 3 pools and each pool has 10 K points. So this subdivision is equally balanced because 30 is I can divide 30 by 3 exactly. So the balance among the pools is fine. But what happens here? That here I'm running the calculations on 5 nodes. So it means that these 3 pools, each of these pools have to be sent to the nodes. And since here I'm using 3 pools and 5 nodes, it means that each pool will be not complete. I cannot completely fit one pool in one node because I have 3 pools and 5 nodes, which means that in order to accomplish the calculation, the nodes need to communicate with each other. So it is much more clever if I use 5 nodes and 5 pools. And you can see the computational time, it is much faster using 5 nodes. Because in this way, I have divided 30 K points in 5 pools, which means that each pool will have 6 K points. And then I can fit one pool exactly in one node. In this way, nodes do not need to communicate with each other because I will never have pools that are split among different nodes. And you can see here that using this configuration, the calculations go much faster. So another trick, another suggestion I can give you when you are using pools with K points, think about what you are doing. Think about that the pools are effective for reducing communications among MPIs. So if you, the more you can fit the pools inside nodes, and the more you can do this exactly, and the faster the calculation. So you have to avoid to have pools that are split among different nodes, because at that point, the 2 nodes, if you have one pool that is split in 2 different nodes, the 2 nodes will need to communicate each other and you will lose performances. So yeah, this is, I think you can think about it as a suggestion when you will be running your own calculation on your own system for production. Look how many K points do you have and think about how many pools you want to use, how many nodes you want to use. If you do this in a clever way, you will see that the computational speed up is really, really significant. Let's check our calculations again. So first of all, I see we have still 5 people who managed to do the exercise. Okay, so I am still running with 4 pools. Okay, now I am here at the last iteration. Let's check whether there are questions. How do Openmp threads and pool interact with each other? Yes, this is another good question. So since we are still waiting here, I think we can also speak about Openmp. So again, now I assume that you are.
Even maybe while you collect the presentation for MP, I can add one point.
Yes, sure. Please, Pietro. Yeah, please.
No, because this is an interesting question that is coming out often. So maybe I wasn't so clear. We mentioned the hierarchy of levels in parallelism, right? Starting from pools that distribute the work on k points, solving the Coniam equation on different k points at the same time. Then our wave function are distributed among many workers. Then there is a lower level of fine-grained parallelism. So that's where Openmp is. It's really used to squeeze all the possible the performance from all the possible subroutines when you cannot further subdivide the data that we have been discussing. So the work on different k points and the wave function themselves. So really, this is in that hierarchy one of the last levels. It enters in that purple box that we were calling fine-grained parallelism. So, and that's it. Please go ahead because you have been preparing very nice work on this Openmp part.
Yes, thank you, Pietro. So we also have Openmp. Let's first see it without, because at this point the risk is to have things are getting more complicated because we have pools, MPI, and Openmp. So let's get rid of pools for now. Let's focus on MPI, Openmp. So calculations at gamma or gamma point. Here I have this example. Of course, let me just say, Openmp, you can see some Openmp speed up, especially for very large systems. So unfortunately, it's something that we could not provide here. We will see something in the next hours, when we will be running GPU's computation. So you will try Openmp there. But with the unless if we don't do very large systems, it is very difficult to see speed up coming from Openmp. So I did calculations for you, and I'm showing you the results here. So here we have an average size system. Here is 32 water molecules and a gamma point. And here I ran calculations using one node, so 48 cores. So my computational facility here is provided with the 48 cores. If you see here, I can choose now whether to use these cores within MPI parallelization or Openmp parallelization. What is the difference? If I use 48 cores with MPI parallelism, the wave function is distributed among 48 processes. So I have the memory is distributed and this is sent to different MPI processes, and these processes have to communicate with each other. Otherwise, if I use Openmp, I will have one single process, but on this process, I will have 48 cores that will be working on it. So please consider that the main basic difference between the two approaches is that with MPI, I am dividing the memory. So my data are divided in 48 batches of smaller batches. And I will have one core working on one batch of data. So memory is distributed and my 48 core. So if I have 48 cores, my wave function, my data, generally speaking, is distributed in 48 smaller batches, and I will have one core per one working on one batch. Otherwise, with Openmp, I will have one single process, so my data stays together, but on that data, I will have 48 threads, Openmp threads, that will be working on them. Quantum Espresso has been natively developed using MPI scaling. So for this reason, MPI, the code has been written specifically for MPI because it is very important to distribute memory when you want to treat large systems, large molecules. Because if the memory is the memory requirement is too much, you are not able to run calculations because you have out of memory error. So for this reason, Quantum Espresso is mainly parallelized using MPI. And for this reason, you see here that MPI scaling is more efficient than Openmp. So because if you also, Pietro told you about the Amdahl law, here I tried to fit this data with the Amdahl law, and we see that the parallel portion with neglecting communication latency, so just focusing on the code, we can say that the parallel portion with the MPI for Quantum Espresso is 95%, whereas Openmp is 76%. So we see that since Quantum Espresso mainly relies on MPI, MPI is more efficient in these calculations. But there is a but. If we go to larger systems, so larger calculations, we can see that Openmp starts to be important. For example, here I have a larger system, 190 water molecules. So this was 32, and here we have 190. And I ran on one node, so 48 cores. And here I did this thing. I asked myself, okay, how should I distribute the cores? So on the leftmost part of the curve, I have one process, 48 threads. On the rightmost part of the curve, I have 48 MPI processes, one thread. And in the middle, I have different portions. So all these calculations have been done using the same number of total cores, 48. But here, I'm mostly using Openmp, whereas here, I'm mostly using MPI. From here, you may notice that this curve is not monotonic, but the minimum is somewhere around here. If I run the same calculations, using two nodes, this minimum here is more pronounced. So here a full Openmp, full MPI. As I said, MPI, generally speaking, is more efficient than Openmp in Quantum Espresso. So I can say, okay, let's just forget about Openmp, let's use MPI. Yes, it is good. Here I have 96 processes, so all my processor cores are devoted to MPI. But here I see that there is a minimum here. If I run with 5 nodes, so increasing the number of the total cores that I'm using, I see that the curve is, is not. Of course, this I didn't mean. Okay. And here I have 6 nodes. So for example, if we focus on the 5 nodes curve, you see that there is a minimum here. So 5 nodes. This is a full Openmp calculation, which means 1 MPI per node, 5 MPI, and each MPI has 48 threads. This is a full MPI calculation, but the best option in this case is this one, is 60 MPI processes and 4 threads, so 4 threads per process. So why is that? This is because, as we said, MPI is very good because it can distribute memory and it is very efficient, but there is this drawback that it involves communications. So the more MPI processes we use, and the more communications will grow, and they will start to, if we use too many processes, communications will start to reduce the computational efficiency. So on the basis on so we have two, yes. So from one side we have communication, the other side we have workload. So increasing the number of MPIs, the workload for each core will be reduced, whereas the communication will increase. So if you keep adding MPI processes, the workload for each process will become very, very small, and communication will grow faster. For this reason, it's not advisable to push MPIs to the extreme limit. But whenever you reach this point in which communication starts to become important, then if you have more cores, it is better to exploit the more cores you have using Openmp, because Openmp still retain a certain degree of parallelism in the code, but reduces communications between MPIs, because here we have 240 processes that need to communicate with each other, whereas here we have 60 processes that need to communicate with each other. So when, of course, there is not a general universal recipe for these calculations. It's just part is with experience, something you can reason about that. And it depends also on the test cases, because of course, with small test cases, you will not see anything. And this is the reason why we did not put any exercise here. But when you move to large test cases, you have to start to think about what you are doing. So if you want, it will happen to you that you will need to use Openmp. In the JavaScript here, you just change this variable, export Openmp num threads. From 1, you set to 2, 3, whatever you want, and you can couple Openmp with MPI. We will see it with GPU's calculations in a while. So yes, I think we have now to move ahead. So let me check here. Okay, 11 people. Okay, my calculation now is finished. And we can compare. That's we change it on, and we can compare here the computational times. 1 pool 9 minutes 32, 2 pools 8 minutes 5, 4 pools 7 minutes, and 8 pools 6 minutes. So we are seeing more or less this plot. I think it's better to go faster, because otherwise, okay, I see that some of you have done the exercise. So for those, I think we can go faster now, because I don't want to, I want to speak about GPUs. So I will just show this other exercise, and we are not doing it together. So the other thing Pietro was telling us was parallel diagonalization. This is another case in which you will see the effect of parallel diagonalization for very large systems, because basically what we have to do is to diagonalize the Hamiltonian matrix. But what we can do when we do parallel diagonalization is to distribute the matrix among different processes, so that we increase the speed of this diagonalization. Of course, as usual, we have the drawback of that communications, because you have to spend time to find a good way to diagonalize the matrix, and then you have to send a portion of the matrix to different processes. They have to do their work, they have to communicate. So this work is worth for very large systems, and it is not the case in our test case. So I will show you now how to do the calculation. If you want, you can try, but I will go fast, otherwise we will not do anything on GPUs. So I prefer to go faster now and do something with GPUs. So I will just explain you how to do the calculation. You just have this keyword now, this option, sorry, this is an MPI run option, and diag4. which means that we are assigning 4 MPI processes for the diagonalization of the Hamiltonian matrix. So it means that the matrix will be divided into 4 pieces. Each piece will be sent to one process, and we will have 4 processes working at the same time to get the eigenvalues. So this is the way you launch the calculations. You will see in the output file this message, subspace diagonalization. Of course, this ndiag4 means 2 times 2, because we are dividing a matrix. So 4, it means that we will do 2 times 2 blocks. And here, if you try the calculation, you will find something similar to this, in the sense that, of course, this is a small system, so we don't see any significant speed up. But we see that, yes, since here we are using 4 pools and 4 diag. Here we have 4 pools, but with 4 diags, the computational time is a bit higher. This is because the system is too small, and also because we are using, yes, the internal Quantum Espresso libraries for parallelization. There are other libraries like Scalapack or Alpha, which Pietro told us before, that can really efficiently do this parallel diagonalization work. I think it is better to skip the exercise now, or at least I show you. I think there is no point to do it now, because it's just that you change your job script and you remove the MPI. I can even show you. So it's just, if you want to run this calculation, you take your job script and you can comment this, and it is enough to change here 4 and the 4, and we keep track this in the log file. So 4 here, 4 here. Then we submit this job and we'll wait a few minutes for it for finish. I prefer to go to the GPU now. So if you do it, you can do. You have time. Okay, the end-on finishes at 12:30, but you will have access to the machines on which you are running. You can run calculations until 1:30. So you will have 1 hour more to run calculations. So I suggest now to go directly to the GPU part, and if you want, you can do the exercise after at the end of the end-on, because you will have 1 hour more. So let's move to the. Okay, so this is Openmp. We discussed it. Let's move to the GPU part. Please. I see 9 people. Only 9 people. Yeah, managed to do that. And I think that other people are running, still running, right? Okay, we have 12 people running and 13 people who managed to do the exercise. Good. So you can lower your lower ends now. And okay. So people who are still running, you just wait and you keep running. And I think the exercise now is clear. And really, I think it is better to move to the GPU part. So please leave your calculation running on the cluster. You will see them later. And look here at the slides again. So the GPU part, again, the 3 things to keep in mind: compiler, linear algebra, and fast Fourier transforms libraries. As Pietro was saying, for compiling Quantum Espresso for GPU, we only have MV Fortran option, because at the moment, this is the only compiler which supports CUDA Fortran, which is the language on which the GPU version of Quantum Espresso has been written. MV Fortran has its own libraries for linear algebra, which are called QBLAS. So BLAS is the usual name, and they added this Q here. So QBLAS libraries manage to run the linear algebra calculations on GPU cores, and the same applies for FFT. MV Fortran has its own version of fast Fourier transforms library, which are called QFFT. So once we load we will say, you know what, the main point when working with GPU and also when running calculation to keep in mind is that each MPI process send its own workload to one GPU. So MPI processes receive a portion of the data and they work on this data. If they have GPUs, what they do is that they receive this portion of the data, but instead of processing themselves the data, they send them to the GPU. This operation is usually called offloading or data transfer, because you really transfer the data from the RAM, from the memory of the CPU nodes to the memory of the GPU cores. So it is really a transfer of data that are written on the GPU memory. But just the important thing you have to keep in mind is that one MPI, the MPI processes receive data, that they are part of the data, and they send to the GPU. The GPU do the calculation, and so the data returned to the CPU. So this here we can see the same concept with the wave function. So the wave function is we parallelize the wave function on the plane wave components. Assume that we have two GPUs. The best practice, the good practice is to use two MPI processes. So we divide the wave function in two MPI processes, and we send each portion to one MPI process, and each process offloads the calculations to one GPU, and the processes will communicate with each other. If you use more than two processes, you have to remember that the calculation is still done by the GPUs. So yes, you can also use 4 MPI processes, but if you have two GPUs, each of these processes will send the calculation to one GPU. So in the best, so sometimes you may observe a very, very little improvement, but most of the times it is negligible, and you will find that 2 or 4 or 6 MPIs is just the same, because the computational burden is on the GPU cores now, and you still have two GPUs. So what rules the bottleneck, let's say, yes, the pivotal part, let's say, the most important part is done by the GPUs. So in the worst cases, if you use too many MPI processes, they will also burden they will also worsen the computational time with the communications. So you are really increasing the computational time rather than reducing it. So the good practice is to use the number of MPI processes equal to the number of GPUs. Here we have exercise 3, which is an exercise in which I wrote a few pieces of code just to let you know what is happening. But I think that we can go fast here, because maybe it is better to run calculations with GPUs. But I will just tell you what how it works, because you will find in the folder, if you want to check later on, you will find the 3 Fortran codes, which basically run a DGEM calculation, so a matrix-matrix product. Code CPU will run it using CPU cores. Code GPU will run the same DGEM calculation on GPU, and code mix is something that I'm going to tell you. So if you run the DGEM on GPU, you can try it. If you can try later on, and you will find that it will take 63 seconds. Exactly the same calculation on GPU, it will take less than 1 second. This is to give you an idea about how faster the GPUs are. So in this case, I think we did the calculations, me and Pietro. It is a factor about 20, which is similar to the speed up reported in terms of teraflops for the Marconi architecture. So the same. So the full CPU code for a matrix product takes 63 seconds. Full GPU code less than 1 second. What happens in Quantum Espresso? Of course, this is an ideal case because, as I said, you also have to consider the time for moving data because as I said to you before, each MPI process offloads data to the GPU memory. So you have to add also this communication. This offloading time to the overall computational time. So if you do this for this ideal case, you will see that the product time for the DGEMM with the GPU is higher than this ideal case, because in this case, we are counting only the time for performing the operation, while here we are allocating the matrix on GPU, on the CPU, moving to GPU, performing the calculation. So what is happening is that here, but also in Quantum Espresso, we are not getting the ideal time, but of course something worse because we have to consider communications. And beyond communications among MPIs, when working with GPUs, we also have offloadings. So MPIs have to move data to the GPU memory. Anyway, we see that from 63 to 0.3 is still really a huge computational speed up. So let's, here, I think now we can go faster. Let's see how to compile Quantum Espresso with GPU. You already know how to do this because we are doing exactly the same operations that we did for CPU. So we go to the Cineca Scratch directory, we go inside exercise 4 directory, we download this version of Quantum Espresso, and you see that in this case we are downloading the GPU version of Quantum Espresso. For this hands-on, we use the version 6.7, in which the CPU and GPU repositories were still kept separated. But in the newer releases, you will find that the code has been merged. So there will be, in the future time, there will be one repository, and you will download one unique source code that can be compiled with both GPUs and CPUs. But at the moment, we still rely on Quantum Espresso 6.7. So you can download this version of QE. You untar this file here. This is the same operations you have done for CPU installation. You change name to directory for your convenience because here the name is more clear. You go inside the newly created directory, and here you load the module files. We see that we are still loading the same modules as before up to here. So HPC Sdk, where Fortran is included. Spectrum MPI for MPI parallelism, FFTW, because these are the FFTs we are using. Here a question could arise, let's see. And a CUDA here, because this is the real difference between CPU and GPU environment setup, because CUDA allows us to really use GPUs. So once you have done it, you have loaded these module files, you can run configure. And we see that in this case, the configure command is a bit more complex because we still have this PGI effort. Basically, we are telling to use the effort, the Intel compiler. But here we also enable Openmp, which we did not do it before. And we are specifying that we are using CUDA. We are using CUDA 11.0 because this is the module that we loaded here. And we are using our GPUs here have a compute capability of 70. this number is given, it depends on the hardware you have, and so it depends on the GPU you have, the underlying GPU core that you have. In this case, Marconi is provided with the Volta 100 GPUs, and they have a computational capability of 70. So maybe older versions of GPUs might have lower values, 60 for Kepler, if I'm wrong. And in the following newer version, we will have, I guess they will have a higher compute capability. You run the configure and you check here again that all values have been taken. I can do this now. So I go in exercise 4. Again, here I first purge module purge. So now I am sure that I have no modules here that would interfere. Then I copy the modules here. So HPC Sdk, Spectrum, FFTW, CUDA, module load. If I list them now, I see that they have been loaded. I run configure in this way. And I'm configuring my version of GPU. Yes, my version of for GPU version of Quantum Espresso. So I think yeah, here we have a good question. I didn't find the FFT libs. Is that because QFFT is not in Marconi and will be internally compiled? Yes, this we will talk a little bit now about this. I guess it is going slow because everyone is doing this configure now. I hope. So could you please raise your hand? How many of you are now configuring the GPU version of QE? Could you please raise your hand so I can say, I can see. Okay, so 15, 17, good. Okay, we have about 20 people configuring. Let's wait so I can. Yeah, usually it is much faster. Now, of course, we are many people running on the same node. So, okay, now my configure is finished. So you can see blast leaves here because, of course, it found the blast leaves. And here we see again that LAPACs, so these two together are for linear algebra. And here we see that these LAPAC leaves have been taken from HPC Sdk. So we are using internal libraries from MB Fortran, which is good because they are because we need the version for GPU, and the GPU version of this libraries is included in MB Fortran. So it is good that here we see HPC Sdk. We don't find FFT libs here just because, as it was pointed out in that question before, because of course now FFTs are done by the GPUs, and is the we use it. It is true that we loaded the FFTW3, but those libraries are for CPU. So the value, the FFTW3 has been overwritten by the fact that MB Fortran has its own version of Q FFT libraries. Indeed, the FFTW3 in this case, they do not appear here because we will be using libraries for GPU now, and they are internal for MB Fortran, and so that's why they are not recognized here. So this is the configure. You should have found, you should have found something similar to this. I think we can skip the compilation step, which of course is just a mechanical procedure now. I don't send this command because we are too late, but of course you can try later on. Make -J4PW, it will compile your version of QE for GPU with these settings that we have just set here. So let's move to exercise 5, so you can see how to run calculations. So this is just the same as we did before. We compile and finally we test the version, and you will find this error, which means that the compilation is working. Let's do now this exercise 5, in which we see how to run a GPU calculation on the cluster. So this is the batch script. You can take it from exercise 5. So here I can go back to exercise 5, and you see here again the README, which is where all instructions are reported, and the job shell. The job script. In this job script is the same that I have pasted here. You will see again two parts: the batch part where we ask resources for running calculations. So in this case, we are running one node again, but 2 tasks per node, because we are asking 2 GPUs. So in the architecture here each node is provided with 4 GPUs, but each of you will use 2 of them because otherwise there is no room for all other people. So you are asking we will ask 2 GPUs per node. And for this reason, we will be using 2 MPIs for 2 GPUs. So this is the main thing to keep in mind. Again, we have the Quantum Espresso executable here. If you have your own compiled version of QE, you can put your path here. Otherwise, you can just leave it untouched because it will point to this folder where we compiled the version yesterday, so you can use it. And here we have again the Openmp setting. In this case, we have 1 thread. And here the MPI run with the usual command: 1 pool, 1 diag, and let's go. The cool thing now is that if I run this, if I submit this job instead, so you can do, of course, you can submit the job shell as is, the input file is just exactly the same we ran in the previous exercise for CPU. So the cool thing now is that if I so now this is running. Remember that before this input file took 10 minutes. So in my case, it was 9 minutes and something. So let's see how it takes, how much time it takes now. You can do this, of course. So okay, 25 people. So I guess you are trying. I think some of you we still have previous calculations running from the CPU exercise, but I think that many people are trying the new one. So in my case, the calculation has already finished. So if I check the output file now, 1 minute, 7 seconds. Let me open here also the other. So it was exercise 2, and for the one, yes, it was this one. So here on the left, you have the CPU test, and on the right, you have exactly the same calculation run with GPU. And you can see, of course, first of all, here, when you run with GPU, you can find this string GPU acceleration is active, and it confirms that the calculation has effectively deployed GPUs. And if I search the same string here, of course, I don't find anything. So you can check GPU here. You also find here the times, the execution times on GPU. But the most important thing is that here it is 1 minute and here it is 10 minutes. So we have just using GPUs, we have used 2 GPUs. So let's go up here. So in this case, we use 16 processors, so MPI processes, and here we use 2 MPI processes. But since in the case using GPUs, these 2 MPI processes offloaded the calculation to the GPUs, which are much faster. And for this reason, here we have 1 minute instead of 9 minutes here. So it is, I guess it is now it is much easier to accomplish this exercise. What you can do now is to add Openmp thread, so you can try them, because the point here is that let me show. Okay, if you change now, what you can do is to change this export here. So here you can put 2 and run the calculation. You can put 4 and run the calculation. If you do this, what is happening here? Because let me compare again. Okay, so here we use 60. So we have 16 processors. Each of us has 16 processors because this is the amount of resources that we asked in the job shell. But we are not using all of them because we are bounded by the number of GPUs. So in this case, we have 16 cores available, but CPU cores available, but we are using only 2 of them because we have only 2 GPUs. So in this case, what you can do is to use Openmp to use the remaining part of the CPU cores that have not been employed in this case. Because in this case, we cannot use 16 cores here because we will mess up with communications because we have only 2 GPUs. So we have to use 2 MPIs. Maybe you can try with 4 but if you use too many MPIs, you will mess up things with communication. So you have to keep the number of MPI bounded to the number of GPUs, or approximately. So, but still we have 16 cores here. So in order to exploit the remaining part of the cores, here it is a good idea to use Openmp. So what you can do now is to run, since these calculations are also quite fast, you can change these Openmp settings here, and you can ask 2, 4, 8 threads. Remember to change the output here. So if you change, for example, 2 threads here, remember to change 2 here, number of threads. I send this calculation again. So I think if you are so I hope that each one of you at least tried to run the calculation with GPUs, because it is, I think it is very interesting if you compare the time between CPU and GPU execution. So now my calculation is finished, so I can compare 1 thread with 2 threads. Of course, here, the first thing we see here is that here we were with 1 thread, we were running on 2 processor cores, 2 MPIs, 1 thread per MPI. So we are using 2 GPUs and 2 CPU cores, and the CPU cores are deployed with 2 MPI processes. Here we are using 4 cores with 2 MPIs and 2 threads. So the number of MPIs is the same here and here, because this number is bounded by the number of GPUs. So I repeat it again, 2 GPUs is better to use 2 MPIs, or you can try 4, but you cannot go too much farther. But you can exploit the rest of the CPUs using threads and Openmp. Okay, in this case, it was even, it took more time than using 1 thread. The test system is small, so I can show you here the final plot. So here I did it, we compare the computational times with CPU, black bars, and with GPUs, a different number of pools and different number of threads. Of course, this test system is small, so as I said at the beginning, you are not seeing any significant. But of course, wait, you can observe a great advantage from using the GPUs in general, because with GPUs, whatever configuration, you are almost 1 order of magnitude lower with computational execution time. Otherwise, of course, we see that from 1 pool to 2 pools, we see some improvement here, because all these bars are a bit smaller than calculations with 1 pool. And with threads, we are not able to see significant advantages. Well, maybe here with 4 pools, we see that the red bar with 1 thread is higher than the other, so using 2, 4, 8. So maybe here we can see something, but honestly, in this case, the speed up from threads is very small, and is something that you can see using very large systems. So I think, yes, again, what I said regarding pools is true even for GPUs, because if you distribute the wave function along plane waves, then the MPI processes will need to communicate with each other. Using pools, the communications are reduced. So this is the end of the hands-on. I would like, since so far I've said many times, oh, you should see with large systems, or you should see with large systems. I think that it could be useful to show you some benchmark test cases on large systems to show the performances. And so this is quite a large system, is 500 electrons. This is thallium oxide or tantalum oxide, I don't remember. And and here we see the scaling with the number of nodes using more GPUs. So here we used 1, 2, and 4 nodes, and each node is provided here with 4 GPUs. And we see that the time to solution is drastically reduced, increasing number of nodes. And here the same with pools. So the pool parallelism, again, we use 1 pool, 2 pools, but here, since we have 26, here we have 4 pools and we are running on 4 nodes here. So when we use 4 pools with 4 nodes, communications are really lowered. And for this reason, here we see a significant speed up using pools. So what we saw with CPUs, it is true with GPUs as well. Here we have an even larger system. So in this case, we have 500 electrons, and here we have 4,000 electrons. And again, we see a very impressive speed up, passing from 2 nodes to 6 nodes. We have to remember that in this, these nodes have 8 GPUs per node. So here maybe I said 4, but okay, it's so each node here has 8 GPUs per node. I have to say that these calculations have been done with the newest version of the GPUs, Ampere family, which has been very recently released by NVIDIA, and these are they have very good performances on double precision floating points. So here again we see this scaling, varying MPIs and pools using 6 nodes. If you use a good combination of pools and MPIs, you can really drastically reduce the computational time. And here we see another test case. This is a very interesting molecule. It's a carbon nanotube with porphyrins, functionalized with porphyrins. So this is a molecular system that is really for production. It's something which you can really use for publishing articles, for doing interesting science. And we have 5,000 electrons here, and this is gamma only. So in this case, we cannot exploit pool parallelism, but we can exploit GPUs, of course. And one SCF iteration on this giant molecule, from our benchmark, from our test cases, it took 90 seconds, run on more than 3,000 core. So running on CPU, if you want to do an SCF on this very large molecule with using only regular CPU nodes, with 3,000 cores, CPU cores, it took 90 seconds per iteration. So 90 seconds, if you need, I don't know, 10, 20 iteration is, is 900 seconds. The same one iteration you can do in 30 seconds using 144 Volta GPUs. These are the same GPUs of the cluster Marconi 100 that we are using now for this hands-on. And the same time, so about 30 seconds, using 24 GPUs of this new Ampere family. So here you are using 3,000 cores here you are using 144 volta GPUs, and here you are using 24 ampere GPUs. So this, I think this can give you an idea of what can be done when all these parallelization strategies of Quantum Espresso are used properly in a smart way. I hope to have given you a few hints about how to use Quantum Espresso and how to exploit HPC hardware and CPU. And I really thank you for the attention. And yes, if you have questions, yes, thank you. Yes, so I think now you can, okay, I don't know now whether that raised hand are for questions or because you did the exercise, but I think I messed up myself because I used that. So if those raised hand are for because you have done exercise, please lower hand. Whereas if you want to do questions, keep them raised. So, okay. So I guess that we have two questions here. Maybe Changpen Lin, is it? Okay, okay, Changpen Lin maybe wants to, is this a question?
Sorry, actually I raised hand because I was doing the GPU calculation.
Oh, okay.
Yeah. Sorry.
Yeah, sorry, it was my fault because I messed up things because I used this raised hand.
Ivan, we have a question from the chat of Zoom.
Yes.
And it's a nice one. What would the CPU do if linear algebra and FFT are done by GPU libraries? So what is the CPU doing?
Good, this is a good question. No, I have to say that there are there are actually small parts of the code that have not yet or have not been ported to GPUs, because what we did was to port the most computationally intensive parts of the code to GPUs. But there are still other parts of the code which remain on the CPU. So there are two cases. When the GPU is working, because the code is processing a part of the code that has been ported to GPU, I think nobody knows what the GPU is what the CPU is doing. I don't know. I think I don't know whether it is just running idle or it is waiting. But it is not important because the main computational burden, not all the computational burden, is done by the GPU. But for those parts of the code that have not been completely ported to GPU, because maybe there are also parts of the code for which is not very important to port to GPUs because we are happy with the CPU performances. So in that case, the CPU is still working, and if you link some linear algebra or FFT library, they will be used for that part.
Yes, there is there are a few portions, and one of them is the FFT. We've been telling that the FFT is done so many times, so a lot of eyes focused on the FFT, and that is one of the few portions of code where, while the GPU is computing, the CPU is doing other things and is basically actually taking care of communication. So this is one portion of code where the CPU and the GPU overlap, doing some useful work at the same time. But then, as Ivan already said, sometimes it's just waiting idle for the GPU to finish. And this is, of course, you may want in general to exploit at best both the CPU and the GPU at the same time, but it's not always so easy, and also not always really useful, because if you see, for example, from Marconi 100, the CPU is very weak while the GPU is very fast. So would really contribute very little. There is a second very important question, I think, and it's probably some misleading number that I gave during my presentation. So please, Ivan, correct me. About n pool on GPUs. Should we be careful on picking an integer fraction of the number of cores of the GPU this time, or should it still be an integer of CPU cores? Now, I clearly made some confusion mentioning GPU cores. So I had to clarify this point, which is very important.
Yeah, yes, it's no, so the point is when you are using pools, what you have to care is about MPIs. And if you are using GPUs, the number of MPIs is kind of bounded by the number of GPUs. You start from how many GPUs can I use? N. So let's fix the number of MPIs. Okay. Then I check the number of K points. Let's see how many pools can I use in order to exploit this my architecture. So when you think about how to run calculation with pools, you just have to think about MPIs. So pools, when you use pools, think about the number of MPIs you are using. But if you have GPUs, the number of MPIs must be equal to the number of GPUs at the first glance, at the first approximation. So the number of cores, which was or GPU cores, is something that is more in depth inside the hardware. So the number of CPU, you never see the GPU cores because the GPU cores are inside the GPU, and they are the reason why the GPU is that fast. So from your perspective, you as a user, but even from our perspective as a developers, the most important point is the GPU as a whole. Then inside the GPUs, you will find cores that are usually organized in multiprocessors or in their ways, but we never work explicitly with cores inside the GPUs, especially when you are running calculations. So from your point of view, you just have to see how many GPUs you have, and then you check it, and then you check how many MPI processes to run. Pietro, if you want to add anything else, please.
No, it was just perfect. And sorry for the confusion. Mentioning the number of workers on the GPU was just to highlight the fact that in general, GPU to run efficiently require more data than CPU. So sometimes for a small input, you don't gain much from the GPU acceleration. That was the whole point. Then forget about GPU cores, please. Yes, there is a final question, probably. I don't know if we still have time. Maybe we're a bit late. Can we?
Well, maybe we have time. Yeah, maybe one or two questions more, and then
okay. Well, I think you are the expert in this field, so this question is really for you. I'm curious regarding band parallelization. I've never obtained speed up from using it on my system. Could you comment on what type of calculation this kind of parallelization is useful on?
Yeah, there are 2 points. There are 2 main aspects. The first point is that in order to see real advantages from band parallelization, you need to have a huge number of Consham states. Otherwise, it is worthless. The second point is there is a band parallelization actually in Quantum Espresso, but it is I think it is not implemented in the it is not really distributing the memory among the band groups, but it is only using it is dividing only the workload and not the memory. So it is I think it has a suboptimal efficiency at the moment.
And it's also used for exact exchange, right? I think band parallelism becomes very convenient with exact exchange.
Yes, because at that time you have to process many couple pairs of bands to compute the exchange integrals. And yes, as much as I know, even in that case, you will see that if you run with proper big architectures and large molecular systems. Let me add a few things. So if you want, you can keep doing the exercises on the Marconi 100 cluster until 1:30, 1:30 CHEST Central European time. So you still have 45 minutes more. You can just take the README files and you read them, and there you are able, you are allowed to submit jobs until 1:30. So if you want to do again the exercises, you want to do them slower, or you want to do even those exercises that we had to skip, or on which I went fast, you can do that. And if you have problems, I will answer you on Slack channel. So you can do this. And regarding the data, if you want to save the data, your working directory from there, you have your account is available until Sunday. So in the next 1-2 days, or maybe it is better if you do now, you better copy the whole directory to your local machine, laptop or a virtual machine. In order to do this, I don't know if you know, maybe I forgot to write this the command in the README files, but I can write you in chat. It is enough that you do this command scp-r, then you, let me do it. So if you go here in I think you can okay. So I wrote you in the chat the command is scp, which means that you are copying the directory, but cp is for copying your local machine from one point to another point. scp, sorry, I forgot it. Obviously, it is missing something. scp minus r user. Okay, sorry. This is the right command. So you run, you open a shell from your virtual machine or from your laptop, and you run scp minus r user is the username you've been using for Marconi 100 cluster. Then at login next Cineca, and this is you give the host name here, and then you copy this directory day 9, which is the directory in which you did the exercises, and dot it means here. Yes, I will. Yes, I will put it on Slack as soon as we close. So you have time until Sunday to copy all your files, so you can keep working until 1:30, and then you have 2 days more to copy back all your directory and files on your local machine, so you can keep them.
I don't see any other questions.
Yeah, maybe we can close. And
well, no, there is another one, maybe. I don't know if we're running out of time, actually. How to run similar job on the GPU. In my institution, they use Lerm. Suggest something to the person in charge. Well, I'm not sure, but certainly if you have so sysadmins at your institute, they can help writing down a job script that allocates and starts a number of MPI processes and also activates, so allocates for your job a number of GPUs. So I think that if you tell your SISSA admin, so the people in charge of the cluster, that you need to run a job with, I don't know, 4 MPI to use the 4 GPUs that you have, they can help setting it up. And by the way, for those who asked about GPU's performance for Quantum Espresso, I linked in Slack a Wikipedia page where you have I think it's the entire list of all cards, of NVIDIA cards. And on one of the columns on the right, there is the performance in single and double precision. And those two numbers are the one that we want to check. You can compare the performance with single and double and immediately realize that there are 2 groups of cards, those where this ratio is about 1/3, and those where this ratio is much larger and double performance is much weaker. Those are the cards where you will not get much out of the GPU. This was a question asked before.
Yes, I don't know if we have, I see 2 raised hand, maybe.
Yes, thank you. I have this question. I've been working recently with this code, Vanilla Berry, from written by Stefan Serkin, and he says that he used a combination of slow Fourier transforms and fast Fourier transforms. I would like to ask you, I don't know if it is the place, why is it better than use only fast Fourier transform? And also is this kind of meshing implemented in Quantum Espresso or?
I didn't get with the alternative of fast Fourier transforms.
He says that he used a combination of Fourier FFT and DFT. Yeah, discrete Fourier transform, which is this low one.
Mm-hmm.
Why he used this combination? Perhaps I just wanted to ask you, because maybe you know.
Well, honestly, what I can tell you is that this is not done inside Quantum Espresso. I don't know exactly the peculiar problem that is optimized with this approach. So I would prefer not to add to give a precise answer, probably because I don't really know the answer now. What is sure is that sometimes even the best optimized libraries and approaches may not be the best option depending on the problem that you want to perform. Let me give you an example in a different context, like matrix multiplication is something that everybody is doing, and of course is something that has been optimized like for so many years by so many people, and eventually we have a number of libraries that, depending on the system that you are considering, can do a matrix multiplication very well. So basically with the matrix multiplication you get basically the peak performance, so the theoretical performance of your CPU, for example. But if your problem is a peculiar size, I don't know, you have very tall matrices, very thin, so the skinny matrices, well, you may gain something from avoiding the general implementation and use some peculiar implementation for your peculiar problem. Now, honestly, I cannot comment more because I don't know the details of this task. So, know if
okay,
you
no,
know something more about this, or maybe someone in the audience.
Okay, no, I was just curious because this code is 1,000 times faster than the post-processing of binary 19. So I was curious why is it so fast. Thank you very much. It was very thoughtful, very helpful.
Thank you. Maybe we have to close now. You can, if you have more questions, you can write on Slack. We will answer there. And yeah, and that's all. So I think we can close the Zoom connection now. Thank you and bye-bye.
Thank you. Bye-bye.
Bye.
Thank you.